Hello, welcome to Advanced Composites. Today is the fourth day of the ongoing week, which is the ninth week of this course, and we will continue our discussion on virtual work today as well as tomorrow and maybe even day after tomorrow, because this is a very powerful technique to solve a lot of problems where closed form methods are not available, and we can get fairly good results if we use the principle of virtual work to solve the problems which are of interest to us. So, today we will discuss another problem in context of composite plates, and we will use the principle of virtual work to solve that problem. So, virtual work method, and here we are applying it to simply supported plate. So, we are slowly making things more complex. So, consider a plate which is simply supported on all four sides, and it is seeing some normal distributed load which is uniform, so it is Q naught, and the plate is especially orthotropic, so if it is especially orthotropic, it means A16 is equal to A26 is equal to D16 is equal to D26, they are all 0, and it is also symmetric. So, that implies the B matrix is a null matrix. The dimensions of the plate are A. So, this is my x axis, this is my y axis. So, the dimensions of the plate are A, and this dimension is B. Let us write down the boundary conditions. So, boundary condition on this axis is W is equal to 0 on all four edges, and on edges x is equal to 0 and x is equal to A, mx is equal to 0, here my equals 0, mx is equal to 0 and my equals 0, and we will not talk about in plane boundary conditions because we are only interested in solving the out of plane problem, and because the plate is especially orthotropic and symmetric, out of plane problem is decoupled because of symmetry from in plane due to symmetric laminate. Okay. So, because the laminate is symmetric, so we will only discuss the out of plane problem because we want to know what is the value of W at different points. Okay. So, now let us look at the governing equation. So, the governing equation for this we have shown in terms of W is this expression. and this is Q naught, because it's uniformly distributed, so it is Q naught. Now, earlier we had solved this problem in an exact way by doing the following. First, we had decomposed Q naught as in terms of its Fourier series component. So, we had decomposed Q naught into Qmn sin m pi x over a sin n pi y over b, and summation of this using Fourier series expansion. And then we also assumed that W is equal to summation of Wmn sin m pi x over a times sin n pi y over b. Okay. So, using this method, and then we solved this, and then we were able to solve this problem. Now, what we will do is we will consider the principle of virtual work to solve this problem. So, we will solve it by virtual work method. Okay. So, what is the first step? The first step is that we have to select W. W is what we want. We have to select a function for W which meets all the kinematic boundary conditions. So, which are the kinematic boundary conditions? W is equal to 0, W is equal to 0, W is equal to 0, W is equal to 0. So, any function which is 0 on all the edges of the plate, that is a valid function. That function need not ensure mx to be 0 or my to be 0 on the edges of the plate, and the function need not satisfy the governing differential equation as well. Okay. So, all we are interested in satisfying the differential kinematic boundary condition. So, we say that okay, W naught is equal to, let us say we will just take a one term solution, W11 sin pi x over a sin pi y over b. Now, this function, it satisfies W naught is equal to 0 at x is equal to 0 and a, and at y is equal to 0 and b. It satisfies, and we do not worry whether it is going to satisfy the differential equation or not. Actually, if you plug it in, it actually does not satisfy the differential equation. Okay. Second, we compute the residue or the error force. So, how do we find the error force? We plug this in the differential equation, and then we compute the error. So, the error is equal to D11 pi over a to the power of 4 plus 2 D12 plus 2 D66 pi square over AB square plus D22 pi over B 4, this entire thing multiplied by W11 sin pi x over a sin pi y over b, okay, minus Q naught is error. So, just to make things look simpler, we call this entire thing in the bracket as D11. So, this is equal to D11, it is not same as capital D11, so this is small d11, W11 sin pi x over a sin pi y over b minus q. This is the error. Third, what is the next step? We have to compute the virtual work, and for computing the virtual work, first thing is we have to select a virtual displacement field, And what kind of virtual displacement field is valid? As long as it satisfies all the kinematic boundary conditions. Virtual displacement is, we call it W1 x comma y, and this function is, it has a small parameter epsilon, an amplitude W111. The last one implies that it is a virtual thing, and we will use a special Galerkin method. So, sin pi x over a, sin pi y over b. So, now using this I compute virtual work and I equate it to 0. So, 0 to A, 0 to B. This is my error force. So, this is D11, W11, sin pi x over A, sin pi y over b minus q times virtual displacement W111 sin pi x over A, sin pi y over b dx and dy. So, this is my entire virtual work, and this should be equal to 0. Okay. Now, if I do this integral again, this parameter epsilon 11 and W111 is common. So, I can ignore this, and then when I do the integration, all x and y, everything goes away, and the only thing I am left is a relation for W11. Okay. So, when I do this, I get W11 equals 16 q naught over pi square into 1 over D11. And if you compare, so what is my solution? So, my solution is W naught x y is equal to 16 q naught over pi square D11 sin pi x over A sin pi y over b. This is a one term solution. We could have used more terms in the system, but this is a one term solution. And if you compare the coefficient of the first term with the exact solution which we had developed a couple of weeks earlier, you will see that this coefficient 16 q naught over pi square D11 is exactly the same thing what we had calculated earlier. So, using this principle of virtual work, we arrive at this coefficient of the first term very easily right away. Okay. This is a very powerful technique. It is not that it will give me exact solution all the time, it just happens in this case that it is giving me the exact solution. The first term value is exactly the same, okay. But in some cases it gives me very accurate results even in the very beginning. So, this is another example I wanted to do today, and we conclude our discussion for today. Tomorrow we will continue this discussion on the principle of virtual work. Till so far we have solved the problem of a beam and also of a plate by using just one term solutions. Now we will see how we can use we can get multiple using the same principle, that is the principle of virtual work. So, that is all for today, and I look forward to seeing you tomorrow. Thank you.